So hello, welcome to another fantastic edition of Math 140 Business. This is, what if you don't have a cited CSUN ID? You don't need a CSUN ID, you just need an ID. So I don't care if it's a license, it's just, you gotta have something that's official. That's difficult to forge and to, fake IDs and whatnot. Doesn't have to be CSUN. Anyways, so we are in lecture number 11 for 140 Business. This is October 7th. And we are working on chapter 11, which is on probability. Last time I gave the axioms of probability. We did some basic examples. Not examples, but we did some basic, the basic axioms. There's 4 of them. Without looking at your notes, does anyone recall 4 basic axioms of probability? Without looking at your notes. Anyone? The 4 basic axioms or rules of probability. Anyone?
Must be between 0 and 1.
It has to be between 0 and 1. Well, what is it? What is it that has to be between 0 and 1? Let's be a little more.
Probability.
Okay. Yes. The probability of any event must be snug between 0 and 1. Okay. What's a second one of our rules?
I believe if a probability is going to occur, then the probability is always 1.
The probability of the sample space is 1. In other words, if you look at the collection of all possible outcomes, and I ask what's the likelihood that one of these outcomes occurs? Well, if it's all possible outcomes, then certainly the probability is going to be 1. Okay. Anything else? There was 2 other ones.
Oh, if it's impossible to occur, something about 0.
Well, we know that the probability of an impossible event is 0. That wasn't really one of our rules, but we can write it. The probability of an event equals 0. Well, actually, let's do it this way, more specific. If E is impossible, then the probability of E is equal to 0. Wasn't one of the 4, but let's throw it in there. What's the one that goes along with it? There was a similar one for the other ends.
If something is possible, it is equal to 1.
I'm sorry, what was it? If E is what?
If E is possible, then P of E is equal to 1.
If E is possible? You're saying if anything?
No, not possible. I mean, if it occurs.
Well, we don't know if it's going to occur. If you're doing a random experiment, we don't know what the outcome is, right? In general. I think what you're trying to say is if E is certain to occur.
Yeah.
Then the probability of E is equal to 1. Again, those weren't the 4 rules that I was looking for, but they certainly are rules. So we'll throw them in there. Okay.
I think
what
one
else?
of the ones that you're looking for is if you want to find the probability of something not happening, then you would do the probability of it happening minus 1.
Good. Other way around, not minus 1.
Well, yeah.
1 minus, right? The probability of something does not occur is 1 minus the probability that it does occur, a very important result. And the last one is if A and B are disjoints, if they cannot both occur simultaneously, then what is the probability of A or B? Anyone recall?
Probability of A plus the probability of B.
Probability of A plus the probability of B. Those are our basic rules of probability. Now, as you go further in probability, if you ever would, There are more rules that can be derived from these rules, or I might impose extra conditions and say, in these situations, what happens? And I might then come up with rules for those situations. Probability is a vast subject, amazing subject, one of my favorite branches of mathematics. It really is a lot of fun. And not always obvious. Sometimes you have to really, to figure out the answer to something, you have to really look at it in a very specific way. Any other way, you can't figure out what's going on, but you look at it just the right way and everything becomes clear. Really a lot of fun. So let's do some examples. What's the probability? Very straightforward, that I roll a 5 if I roll a fair die. What's the probability that I roll a 5 if I,
1 in 6 chance.
1 out of 6 chance, but you're assuming something here. I mean, we said it's fair, and that fairness is key, because just because there's 6 chances that something can occur, or 6 outcomes possible, one of which that you're looking for, does not automatically make it 1 out of 6. What's key here is, since the 6 outcomes are all equally likely. The 6 outcomes are all equally likely. Because the 6 outcomes are all equally likely, that's why it's 1 out of 6. But just because there are 6 outcomes does not automatically make it 1 out of 6 each. If I have a bag of marbles and I have 100 blue and 17 red and 26 green, and I have all different numbers, and I say, what's the likelihood that you pick a green? You don't say, oh, there's 5 colors, it's 1 out of 5, because you obviously have to take into account that there's more of one color than another. So this idea of 1 over 6 relies upon the fact that they are all equally likely outcomes. If we did not have that, it would just not be true. Now, what's the probability that you don't roll a 5?
5 out of 6.
5 out of 6. You can do it in 2 ways. One is to use this rule above that says the probability that something does not occur is 1 minus the probability that it does occur. Or you can always just ask yourself, well, how many ways can a 5 not occur? It could be a 1, or 2, a 3, a 4, or a 6. There's 5 out of 6 ways. So you can do it directly, or you can do it indirectly. But of course, either way, you better get the same answer. If I say the probability that I roll a 7 from 2 dice, what is the probability that I roll a 7 if I roll 2 dice? Well, how many outcomes are there if you roll 2 dice?
12.
12 outcomes. What are they?
Isn't it 0?
If you roll 2 dice, you can't roll a 7? I mean a sum of 7. When you roll 2 dice.
7.
Yeah. I mean, when you roll 2 dice, it's usually I just assumed, I'm sorry. When you roll 2 dice, it's the sum that you care about. So someone said 12, 1 out of 12. Why? What's 12?
Oh, I think it's wrong. I just added 6 and 6 because there's 2 dice.
I see. So you added 6 and 6. So you said there's 12 outcomes. And of those 12 outcomes, how many of them are 7s?
2.
What are the 2?
Oh, actually, no, because there's 6 on a dice. Never mind.
Okay, so the first question we have to ask ourselves is the denominator. How many equally likely outcomes are there if you roll 2 dice?
36.
36. Because how many outcomes are there for the first die?
18. Oh, wait. Oh, sorry, 6. 6. 6 dividing it.
Okay, I was gonna say, what kind of dice do you play with? All right, there's 6 outcomes to the first die, correct?
Yes.
Now, for each of those 6, how many outcomes are there for the second die? Six.
Okay.
That's why it's 6 times 6, not 6 plus 6. 6 outcomes for the first die. Each of them has 6 for the second die. 6 times 6 is 36. Of those 36 outcomes, how many of them would give you a 7?
2,
What are the 2?
3, and 4, and then 6 and 1.
And you forgot 5 and 2, or you just don't think it counts?
I forgot 5 and
So what's your answer?
3.
Okay, it's actually 6. But why is it 6?
Because you can get a 5 on one die and a 2 on the other, or you could get a 2 on the first die and a 5 on the other, and same for all the other options.
Correct, right? 1 and 6 and 6 and 1 are technically 2 different outcomes. 2 and 5, 5 and 2, 4 and 3, 3 and 4. Right? You can see that better if the dice are colored. If one's red and one's blue, then certainly a 4 on the red and a 3 on the blue and vice versa would be clearly different. Correct?
Yes.
Okay, so you have to take that into account. So it's not always necessarily obvious, but upon some thought and reflection, hopefully that's clear. We all agree? And you can ask lots of basic probability questions, and some of them are more fun than others. But it's not really until you get to probability models that things get a little exciting. So what exactly is a probability model? It is a collection of outcomes called the sample space. We've already seen this. Together with their corresponding probabilities. It's not enough to say, oh, my outcomes are 1, 2, 3, 4, 5, 6. That's not a probability model. That's just a sample space. If I roll a die, if I roll a coin, a die, I was right the first time. If I roll a die, 1, 2, 3, 4, 5, 6. That's my sample space. But you haven't told me my probabilities for each of those outcomes. If you say 1/6 each, now I have a probability model. Okay, I need the collection of outcomes and I need the corresponding probabilities. It's the two of them together that give me my probability model. Now there's two types of probability models. There's finite or discrete, and there is continuous. And these are very different from a mathematical perspective. For continuous, you need calculus. For finite discrete, you need algebra. So because this is a non-calculus based course, we are going to limit our attention for the most part to the finite discrete scenario because we don't have calculus at our disposal. Unfortunately, we can't completely avoid it because you still need some continuous models to really do probability and statistics the right way. So we'll have to do it a little bit. But right now, we're going to focus our attention on finite discrete. So what exactly is the difference between finite discrete and continuous? What's the situation of a finite/discrete model versus a continuous model? So in a finite model, there's only a finite number of outcomes. For example, if I roll a die, how many outcomes are there?
6.
Is that finite?
Yes.
Yes. If I flip a coin, how many outcomes are there?
2.
Is that finite? Anyone?
Yeah.
Yes. Okay. These questions are not hard. So I would love it if I had actual participation from more than just 2 people. If I tell you to go outside and walk the full length of a basketball court and throw basketballs until you make one into the net on the other side of the court. What are the possible outcomes for how many throws it will take? Give me some possible outcomes for that, for how many throws it will take.
Infinity.
It could take infinitely many throws,
Yes.
but infinity is not really a number, so you can't really have infinitely many throws.
500,000.
You can have 500,000 throws, that's a possibility.
One.
You can have one throw, that's a possibility. Can you have 7 throws?
Yes.
Yeah.
A million?
Yeah.
A billion?
No.
It's not possible? Or it's not probable?
So much today.
It's not possible.
Probable.
Why is it not possible to take a billion throws to throw it in?
Because who has time for all that?
Oh, okay, so now you're taking into account, temporal logistics, which is certainly a valid point. That's certainly valid, but let's assume that you can freeze time just for the sake of this argument. The point I'm trying to make is this is not a finite probability model because there's no last number that you say, that's it, up until this point, but no further, like there is with a die or a coin. It can keep going forever. It's not finite. But at the same time, it's not continuous because 1, 2, 3, there are gaps between them. You can't have 1.7 throws. Discrete means that there's gaps. You can count them. You can separate the options. So this model is not finite, but it is discrete. And the discrete case and the finite case are similar mathematically. So we lump them together. What's an example of a continuous model? Something where the outcomes are not separable, but they're every number, no matter how many decimals you want to throw in, we can theoretically get a different value. Continuous with no breaks. What's an example of something that might be a continuous model?
Probably growth rate when you're taking into account like every like second.
Okay, so if I'm measuring the height of a person at random, and then in theory, that person could be any height between some lower value and some upper value, right? In theory. I might not have the measuring instruments to determine the 10th decimal, the 100th decimal, the millionth decimal, and so on. But in theory, at least, every number is a possible value. It's a continuous model. If I'm waiting for the bus, and the bus can come anytime, could it come 1 minute from now? Could it come 0.7 minutes from now or 1.364 minutes from now and so on? Again, the answer is yes. I might not have the measuring instruments to get to those decimals if I really want to keep going, but in theory, the bus can come at any time. That's a continuous model. Does that make sense?
Yes.
Okay. Again,
Yeah.
so the mathematics for finite and discrete is different than the mathematics for continuous situations. For finite and discrete, for finite and discrete, you can calculate the probability of any specific outcome. For finite and discrete, you can calculate the probability of any specific outcome. For example, if I roll a die, what's the probability of getting a 6 or a 5? It's 1 out of 6. I can calculate that. But for continuous, you can only calculate probabilities of what? You can't calculate the probability of a 1.3 because to the infinite decimal, it's virtually impossible to get exactly 1.3. Maybe you'll get 1.30000000426 and so on. That's not 1.3. You can't get individual values when it's continuous. So what's the next best thing if I can't get individual values? What's the next best thing if I cannot get individual values?
Is it fractions?
Well, but again, even a fraction is a specific value. Like if I'm waiting for the bus, let's say the bus is going to come any minute. I can't calculate the likelihood that it's going to come exactly 1.3 minutes from now. I can't do that because 1.3 exactly is too fine of a value. So what can I do? What can I calculate? Or in theory, what should I be able to calculate in the case of the bus? If I can't do specific values, what's the next best thing?
Range.
Ranges of values. Can only calculate probabilities of intervals or ranges of values or of outcomes. So for example, waiting for the bus where it's known, and I use known in quotation marks because how exactly would you know this? Where it's known the bus can come any time between now and 10 minutes from now. And furthermore, any time is as likely as any other. So I'm waiting for the bus. It's known the bus can come anytime between now and 10 minutes from now, and any time is as likely as any other. What's the probability that the time that it arrives is between 3 minutes and 5 minutes from now? We haven't technically learned this, but let's see if you can divine the answer. You're waiting for the bus. It can come anytime from 0 to 10. It's equally likely to come at any time. What's the likelihood that it comes between 3 and 10 minutes from now? Who would like to take a guess? Even if it's wrong, I would love guesses, educated guesses. Don't say like banana. That doesn't make any sense. Make it an
3
educated.
out of 10.
How much?
3 out of 10.
Why 3 out of 10?
Because it could be 3, 4, 5, and out of 10 minutes. I just took a guess.
Okay, well, it is out of 10 minutes. I agree with you that. But 3 out of 5, 3 to 5 is not 10 minutes. How many minutes are there between 3 and 5?
2.
3.
It's 2 minutes, not 3. If your clock strikes 3, and then you wait until your clock strikes 5, how many minutes have gone by?
2 minutes.
2 minutes. Right? It's not 5.5 or 5 1/4. It's from 3 to 5. And how do we do that? How do we do that? We kind of imagine the following scenario. Here's 10, here's 0. It's equally likely to be anywhere from 0 to 10. So I make a little graph with the same height everywhere to indicate equal likelihoods everywhere. Here's 3, here's 5. So tell me graphically what this calculation should look like.
they should just take into account the whole gap in between 3 and 5, including 3 and
So if I look,
use-
if I look at the gap between 3 and 5,
just fill it all in.
so that's between 3 and 5. What part of that shading would indicate an answer of 2/10?
The bottom part, x-axis.
So maybe I'm not being clear what I'm asking for, but I want to know where this value 2/10 came from. Not just the 10, but the entire value 2/10 in terms of this picture. Is there something in this picture that would indicate that the answer to this question should be 2/10?
Because between the 3 and the 5, it's like 3 to 4 is one, and then 4 to 5 is another one, and then the rest of the graph is like 8, and then you would add up the 2 plus the 8, and that's your denominator.
Yes, yes. So the area of that divided by the total area. This is the area of that divided by the total area. When it comes to continuous models, it's all about the area under the curve. If the area under the curve is 10 and the area that I'm interested in, 3 to 5, is 2, then the probability will be 2 out of 10. The area that I'm looking for divided by the total area. Now, this is great for rectangles or triangles or trapezoids, even circles to some extent. But what if I have a shape that looks like this? How do I find the area under the curve of a normal curve?
With an integral.
Yes, there we go. Back to calculus again. Whee, calculus. Which of course is not a prerequisite for this class, which means we're going to have to use calculators or tables or programs online, but we cannot do continuous models other than the simplest types. We cannot do continuous models by hand without calculus. So we're going to be limiting our attention for the most part to things that we can use by hand, like this one, or to things that we can use the calculator for, like that one. Okay, but if I give you some random shape and say, what's the area from here to here? You cannot do that without calculus, so don't even bother trying. So, some examples of continuous models. We just had 2 of them. Examples of continuous models. One, of course, is the normal. In fact, if you go back to that chapter on the normal curve, perhaps you'll recall, how did we find the area under the curve? We used our calculator. We used some program like Crunch It, or we used some table that gave us the answer because we can't do it by hand. The other one that we did already just now is called the uniform distribution. The uniform distribution is the one that's the same height everywhere. The difference between the uniform and the normal is, for the normal, it's most likely to be somewhere in the middle. And the further you go from the center, the less likely an outcome you expect to get. The uniform, you are just as likely to get any result as any other result. Do you recall? I think I did this. I think I showed you this. Did I show you this applet online with different shapes? Did I do that? Anyone recall? Bueller, anyone there?
Wait, what?
Did I show you this? Did we ever do this website?
It's not showing.
Yeah, I don't see anything.
That might help if I shared my screen. Okay, how about now?
Yes, you did show us this.
Okay.
Yeah,
Okay, so 1 is a uniform distribution. It's got the same height everywhere. And therefore, if I take lots of data points, I would expect in the vicinity of each number occurring just as often as any other number. And as you can see here, it's certainly ballpark, correct?
Yes.
Okay, number 5 down here is the normal distribution. We've done that before as well. Again, here's a situation where the ones in the middle are much more likely to occur than the numbers on the end. So what do we expect? We expect lots of results near the middle and not so many results on the left and the right. Then there's some weird distributions like this one. A situation where I expect lots of results on the far left, lots of results on the far right, and not many results in the middle. Is there a real life scenario that will be modeled by this distribution? I'm sure someone can come up with something. I don't know. Anyone think of something? A random situation, you don't know what the outcome is going to be, but small numbers and big numbers are expected to occur a lot, whereas medium numbers are not. Can anyone think? What?
Hospital visits.
Hospital, yeah. So we spoke about this before, right? Hospital visits, right? Babies or young children, you know, they go to the not podiatrist, the pediatrician, right? So they go to doctors when they're younger. Old people go to doctors a lot because they're sick, they're failing, and people in the middle not so much, right? So this is a reasonable model for that situation. And all these other ones. Number 8 is a very important one. This is one of the most important models out there. It's called an exponential distribution. Very important. Can anyone think of a model where small numbers occur lots of times, and the further you go, the less likely of an outcome you're going to receive? A situation where small numbers occur a lot and big numbers don't occur that much.
Lottery ticket,
Lottery tickets? What do you mean by that?
like the probability of taking home a lot of money from one. You're more likely to gain a little bit from them than you are to gain a.
Well, I mean, in this case, what would the number 0 or the small numbers being referring to versus the large numbers? How much you win?
Yeah, possible. The possibility.
So a lot of people win 0, and a few people win a small amount because there's those minor prizes. But as the prize amount goes up, the amount of people winning drops down significantly. I can see that. I can see that. It might not look like exactly like this shape, but I can certainly see something like that. But again, that's the whole point. There's lots of models in the world for different scenarios. And different models come with different shapes. And if I want to calculate the probability of landing between like 10 and 20, I'd somehow have to calculate the area under the curve from 10 to 20 and the area under the whole curve and divide. And that would give me the probability of being between 10 and 20. Of course, the area under the whole curve is always 1. That part's easy. So it's just finding this part here, and that will be my answer. So that's how we do continuous distributions. Finite distributions are in some sense easier in that we just count, but harder in the sense that it might be a little paradoxical, but once you know calculus, integrals are a lot easier than adding discrete values. It's you know, people who don't know calculus might be a little surprised by that. And people who just learned calculus and haven't really done a lot of it might be surprised by that. But it turns out if you know calculus well, calculus computations, if they're possible, are usually a lot easier than infinite sums. So it's actually a lot easier to work with continuous models than it is to work with discrete models. So let's do a quick example. Suppose x, which is the height of a woman is normal with a mean of 64.2 probably inches and a standard deviation of 2.8 inches. Okay, so capital X represents the height of a woman, a random woman chosen, and we're told that it's a normal distribution. If we didn't have that, we'd be out of luck, but we're told that it's normal. And the question is, what is the probability if we pick a random woman that her height will be somewhere between 68 inches and 70 inches? What's the probability if we pick a random woman that her height will be somewhere between 68 inches and 70 inches? So how would I do a problem like this? How would I calculate the likelihood that a woman's height is between 68 and 70, given the information provided?
Wouldn't it be finding the z-scores first?
So if I don't want to use my calculator and I go to a tables, I would need to find my z-scores.
Okay.
If I want to use my calculator, I can skip that part. Do we want to use a calculator or do we want to do it from the tables? Calculator. So how would I do it on the calculator?
You could do it through you go to second district and then go to normal CDF.
Yeah. And then put in what?
You'd put in I think 68 and 70, like 68 for the low, 70 on
68 for the low, 70 for the high.
and you just fill in the mean 64.2 and then the standard deviation to 2.8.
And what do I get?
Let me put it in real quick.
I got 0.068, 2.
Yeah, so the book is 0.0677. Again, as long as you're ballpark, rounding, whatever, it's all good. But there's a 6.77% chance that if I pick somebody at random, if I pick a woman at random, that she will be between 68 to 70 inches. How do I do that? With a calculator. This is not done by hand. Even if you want to do the z-score approach, you still don't do it by hand. You go to tables. You don't do this by hand. Even with calculus, you can't do this by hand, by the way. Those of you who know calculus, hopefully you know that not every function has an integral. And it turns out that the normal curve does not have one. You cannot integrate it. The best you can do is use software that approximates the integral, the area under the curve. This is not doable. Okay, questions?
I
Sorry, what was that? All I heard was blah, 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 blah.
I'm sorry. I just wanted to know, when you plugged into the calculator, what was the upper bound?
70,
Okay.
right? We're doing 68 to
Okay,
70,
thank you.
right? 68 to 70.
Professor,
Yes,
I got 0.0682.
there were 0.0. Yeah, okay. So what do you plug in exactly?
This my lower was 68, my upper was 70, mean was 64.2, and the other one was 2.8.
Okay, well, that tells, so what do you get again?
0.0682.
Okay, so that tells me then that the answer from the book was from tables where they're not as exact as your calculator. So your answer is better than the book's answer. It's close. You're only, 0.5% off. But if you use the tables, since you don't, if you calculate the z-scores, it's not going to be exactly at a point. The calculator is a little bit better in that regard. Okay, but it's same ballpark. Agreed?
Yeah, thank you.
Okay. So that takes us to the end of chapter 11. Which means note to self, put up 11 homework tonight. And let's start chapter 15 on the sampling, distribution of a proportion or for a proportion. The sampling distribution for a proportion. But before we do this, I want to go back to that website and I want to illustrate something on it. So let's look at number 3. Okay, you can all see this, right? Am I sharing?
Yes.
Okay.
Yeah.
If you look at number 3, would you say that this graph looks like a normal graph? Does this
No.
graph, no, right? Not even close, correct?
That's correct.
Not even close. You're very likely to have small numbers. You're moderately likely to have big numbers. You're very unlikely to have middle numbers. This is not normal at all. This is taking one at a time. So whatever model this is from, whatever situation, I sample one at a time. I have lots of small numbers, some big numbers, a few middle numbers. What if instead of sampling one at a time, I sample 2 at a time and I average the results? Do I expect the shape to look exactly the same?
No.
Let's see what happens. Very different, correct?
Yes.
And if I did 3 at a time, would I expect it to look like this?
No.
Well, if I do 3 at a time, if you remember what 2 looked like, then 3 looks a little different. And if I do 4 at a time, that's going to look a little different.
They get closer and closer to normal.
Do they get closer and closer to normal? Well, let's
Like
take a
the
look. Well, let's do 5 at a time. Does that look like a normal curve to you? 6 at a time?
It's getting there.
It's getting there. It certainly is. And by the way, even though we haven't gone that far yet in the book, it's not that far off, but we haven't actually done it. This is the central limit theorem of statistics. The central limit theorem says that whatever the shape of your underlying distribution, no matter how weird it looks, if your sample size gets large enough, your sample distribution will start to look normal. We see by 8, I think we would all say, if I had to say, what shape is this? You would say, oh, that looks normal, right?
Yes.
So if we go to 4, certainly not normal. Let's see how long it takes for this one, which is like almost the opposite of normal, to turn normal. Let's go to 2. If I do 2, that's very different than 1 already, but not quite normal. If I do 3, well, I feel like those humps are kind of getting closer together in the middle. 4. Is it normal yet?
No.
5. So stop when you say, yeah, that's normal. No, not quite there. 6. What do you think? Would you call that normal?
Yeah, that's pretty normal.
That's pretty normal. So already by 6, we got close to normality. I mean, certainly if I go up to 30, which is the maximum that the Apple can handle, 30, certainly it's going to look normal. But even by 6, it was already looking normal. So the central limit theorem says, no matter the shape of your underlying distribution, let's even do 2, right? This looks very weird shape. Almost the opposite of an exponential. Here we want big numbers, not small. Let's go to 6. That was when we saw normality for the other one. Already by 6. That's actually very normal. Wow. 5.
So what is the increasing the sample size do exactly?
What does increasing the sample size do? It's a great question. So let's understand wow, look at this. Even by 4, we have almost normality. I mean, you got a tail here, but it's not bad. So let me explain what increasing the sample size does. And I will illustrate it in the context of this distribution, which is the uniform distribution.
Okay.
Okay, here we have a case where every number is equally likely, right? So 0, 50, 100, they're all equally likely. So let me ask you a question. If you picked one number from this distribution, which number would it most likely be?
Well, there's some that are more likely than others, but they're all like relatively like.
Well, they're only more likely because this was the result of our actual experiment. Okay, but if I'm not looking at the result, I'm looking at the underlying distribution itself. What number would you expect to get if you picked one number?
They're all equally likely.
They're all equally likely, right? There's no one number that stands out as being more likely than any other. Now, if you to take 2 numbers and average them, how likely is it that the average of 2 numbers would be a 0? Let's think about what it takes for the average of 2 numbers to be 0. Both of them would have to be 0, right?
Correct.
Now, one number being 0, it's as equally likely as any other. But if every number is as equally likely, think about rolling doubles and dice, right? 1, 2, 3, 4, 5, 6. They're all equally likely. But rolling double 6s is a lot less likely than rolling 1 6, correct?
Yeah.
Which means when you average 2 numbers, and think about dice. Let's just do that example. When you roll 2 dice, each 1 through 6 equally likely as any other, what is the most likely outcome when you roll 2 dice? In terms of the sum, what is the most likely outcome?
7.
7. What is the next most likely outcome?
6 and 8.
6 and 8. What's the next most likely outcome?
5 and 9.
5 and 9. They get progressively less likely as we move out from the center, correct?
Exactly.
Oh, even in a situation where every outcome is equally likely, when we do 2 at a time, we expect to get values in the center more than we do on the edges, correct? Let's see what happens when we do 2 at a time. Does that jive with our intuition based upon what we just spoke about?
Yes.
So when you increase the sample size, what's happening is you make it more likely to get numbers near the average, near the center, and less likely to get numbers on the wings, which is exactly what the normal distribution claims. Right? The normal is very likely to be in the middle, not so likely to be on the edges. So when you increase the sample size, you're on the way towards making the sample distribution look normal. And this is what this chapter is all about, the difference between the actual population distribution, where you do 1 at a time, and the sample distribution, where you take samples of size 2, of size 3, of size 10 at a time. Does that make sense so far?
Yes.
Okay, so what we have here is as follows. We're going to start with the difference between a parameter and a statistic. A parameter is a number that characterizes some aspect of the population. Usually not known. If I know the parameter, why take a sample? The whole point of a sample is to approximate parameters. What's the average height of every American? I don't know. I'll take a sample. So a parameter is a number that characterizes some aspect of the population. A statistic is a number that characterizes some aspect of the sample used to estimate a parameter. So what's a statistic? It's the average of my sample. What's the parameter? It's the actual average of the entire population. Why am I taking my sample? Because I want to approximate the true value, which I don't know. So the parameter is unknown. I don't know it. So I will use a statistic and I will try to calculate it. Does that make sense?
Yes.
Now, in this class, there's essentially two scenarios that we're going to focus 99% of our attention on. Two cases. Case one, the parameter is equal to P, equal to the true proportion. What percent of Americans will smoke? P, 18%, 13%, 26%, whatever number it is. That is the parameter. It's the true proportion from the entire population. So what is my statistic going to be? Well, it's going to be my sample proportion. I'm going to take a sample, and hopefully my sample will be representative of the entire population, and my average from my sample or my proportion from my sample will be a good estimate. And I'm going to use a symbol P hat. So P hat is the sample proportion. Make sense?
Yes.
Okay. Case two. The parameter will be mu, the true average. What is my statistic? What is my sample average called? What symbol do I use for my sample average? Anyone recall? We've done it a few times. What do I think we've done it. What do I use? What symbol do I use for my sample average?
Is it like a line on top of
Line on top of what?
the same new symbol or no?
Well, we don't use mu, but we've used, I think, X bar. We've used that before, correct?
Yeah, that's it.
Right. So the two cases that we're going to focus the majority of our attention on are parameters, our proportions and averages. There's the true proportion, don't know it, so I take a sample. P is a true proportion, P hat is my sample proportion. Hopefully that's pretty close. Mu, the true average, X bar, the sample average. Hopefully that's pretty close. The law of large numbers says, the law of large numbers says as follows. As the number of observations increases, the sample proportion P hat gets closer and closer to what?
To P.
To P, to the population proportion P. Now, let's think about what this means. If you flip a coin, a fair coin, what outcome do you expect to occur? If you flip a fair coin, what outcome do you expect to occur?
Heads or tails?
Heads or tails, equally likely. I don't expect anything. It could be either one, correct? If I get heads on the first one, then what do I expect for the second one?
The second one. Oh, wait, if you get heads on this one, that's the tails.
If I flip a coin and it becomes heads and I flip it a second time, what do I expect the second one to be?
Tails.
No, I do not.
Why?
Well, does a coin have a memory? Does the coin say to itself, oh, I was just heads. Oh, let me do tails now to even it out?
No, yeah.
No, so as far as the coin is concerned, nothing's been done before. It's a new flip. It's a first flip. Right? So if I get heads on the first one, the likelihood of heads on the second one is still 50%. And if I get two heads in a row, what's the likelihood of heads in the third one?
50%.
50%. So I cannot predict with any certainty what the outcome is going to be on any specific flip. But if I flip it 1,000 times, what can I expect?
You can.
It should be relatively 50%.
It should be relatively 50%. In other words, while you can't predict anything for any one experiment, the law of large numbers says as the number of observation increases, the sample proportion is going to get closer to the true population proportion. Which is I think it's very cool that on any one thing, you can't tell me anything, but on all of them together, you can. And this is a mathematical fact, by the way. The law of large numbers is not just a conceptual idea. You can prove it mathematically, of course, as usual. What do you think you need to prove it?
Calculus.
Calculus, so we can't do it. And not just calculus, by the way, you need some more advanced stuff as well. But the point is that this is a fact, okay? As the number of observations increases, the sample proportion gets closer and closer to the population proportion P, okay? Does that make sense? Or at least intuitively, does that make sense?
Yes.
Okay, so next. Hopefully this is yes from everyone, although I have basically two people talking, so I don't know if any, you know what, let's say something in chat if you're there. Just so I know that I'm, actually having, yo, what up? Banana's good, hi. What else we got? So let's see what your imagination, everyone. Come on, I have banana so far. I have yo, got a smile, ice cream. Ice cream is not Jensen's is what, go Dodgers. Oh, Lorena, you had to? Seriously? Really? FY.
Yes, really.
I'm going pumpkin spice. What the freak is your? I don't know. Okay. Jordan, I like it. Okay. All right. Ira's praying. Okay, I got some people here. Hopefully you guys are all listening and don't just wait for me to berate you for not talking or something. Now is that an unhappy face or a smiley face? That's a smiley face. That is I don't know what that is. What is that? Is that a ghost? Is that Casper? Is that Casper? That's another cartoon from my Casper the Friendly Ghost. Oh, good old Casper. Anyways, so huh? You don't know Casper?
I've seen the live action movie probably, but
well, I was based upon a cartoon. What the Anahita? I don't know what that is, but that's kind of
It's a moon. It's a smiling.
What is that?
It's a moon.
It's a moon?
Yeah, and he's smiling.
Okay, I believe you, but I don't see it. But that's okay. That's okay. I like your ingenuity. So, population distribution versus sampling distribution. as we saw, the shape of the population distribution is not necessarily the same shape as the sampling distribution. We know that for a population distribution, there's going to be a mean mu and a standard deviation sigma. Let's go back for a second to that applet. It's a very useful applet. I use it a lot. And let's go back to pick any one of these 8s, except for number 5. Pick anyone besides 5.
7.
Okay, 7. So when I do 7, what's the mean? Oh, someone said 3. Do we have access? Yeah, this is a website, by the way. This is the website. I just did a Google search for applet central limit theorems. And the very first one, this HTTP 195.134.76. This is it. Okay, it's just a let's do 3. 3 is more fun anyways. 7. So, oops. Okay, so what's the mean of the population distribution?
44.
44.1. If I do 2 at a time, what's the mean?
40.
43.9.
If I do 3 at a time, if it lets me, if I do 3 at a time,
44.1.
44.1. If I do 4 at a time, what do you think the mean is going to be?
A little higher.
Higher. Well, let's take a look.
43.9.
44.0. By the way, remember, these are samples. These are not true values. So, if you're off by 0.1 or 0.2, it's basically the same thing. So what can you say about all these means? Essentially.
They're about 44.
Yes, they're about the same. The mean of a sample distribution is the same as the mean of the population distribution. But what's happening to the standard deviations as it goes up? Let's go back to the first
Going
case.
down.
It's going down. Exactly. If you look at the standard deviations, the standard deviations go down as the sample is 34.4. Then we do another one and it becomes anytime now, boys. It becomes smaller. Oops. Oh, no. Okay. If I hit it a bunch of times, it goes fast. There we go. 3 times, smaller 4 times, smaller 5 times. So notice that the mean is basically staying the same, but the deviation is getting smaller every time. You see that?
Yes.
Yeah.
So as a general rule, whatever the mean of the underlying distribution is, the mean of the sample distribution is going to be the same. But not so for the standard deviation. What do you think happens as n gets larger? What happens to the standard deviation? It gets smaller. Now, the actual math is that we get the original divided by the square root of n, which we're not going to prove because it requires a. So we're not going to prove it. It's just a fact that whatever the standard deviation is of the population distribution, when you do a sample of size n, you divide it by the square root of n. This is for averages. What about, this is one case. This is for averages. This is for averages. What about for proportions? What about for proportions? So we have the true proportion, P. That is the true proportion, which we don't know. And then we have the sample proportion, P hat, right? So the question is, what is the mean and what is the standard deviation in each of these two examples? So the mean is just P and it stays P, because just like the first case, the mean doesn't change. I don't know what the mean is, but whatever it is, it's the same mean for the proportion as it is for the sample proportion. The standard deviation, though, is a little different. In this case, it's the square root of P times 1 minus P. You multiply P times 1 minus P. In this case, it's P 1 minus P over N, again, in a square root. So we have the same results, which is divide the original standard deviation by the square root of N. That gives you the standard deviation for your sample proportion P hat. And the mean stays exactly the same. So let's do an example. Let's do an example to illustrate this. Okay, it says here, although over 50% of American adults believe the maximum that breakfast is the most important meal of the day, over 50% believe it, only about 30% eat breakfast daily. So about 30% eat breakfast daily. Select an SRS, a simple random sample of 1,000 American adults. Okay, we're taking an SRS of 1,000 American adults. The question is, I'm trying to phrase it in a way without just reading it word for word. What percent of those what percent of samples of size 1,000 would give a p hat between 0.272 and 0.328. Okay, so select an SRS of 1,000 and do this over and over and over again. So select an SRS of 1,000 and do this lots of times. So select an SRS of 1,000, calculate your p hat. What proportion in that sample eat breakfast? Do another SRS of 1,000, calculate your p hat. Do another SRS of 1,000, calculate your p hat. Do another SRS of 1,000, calculate your p hat. Keep doing it over and over and over and over and over and over and over again. What percent of your p hats are going to be between 0.272 and 0.328? Okay, that's the question. What percent are going to be between 0.272 and 0.328? So the first thing to realize is with a sample of size 1,000, remember what we learned, what we saw in that applet, that whatever the distribution looks like for small n, if n is large enough, it looks normal. So for samples of size 1,000, can we assume normality?
No.
Well, in the examples that we looked at, by 6 and 8,
Oh, okay, yes.
we were already getting normality, right?
Yeah, okay, now I get what you mean by the SRS.
Right? So by the time we reach 1,000, we're certainly in the range of normality. Agreed?
Yeah,
So that means that p hats is normal with a mean of 0.3, approximately at least. That's the mean, all right, mu equals 0.3. And what is my standard deviation gonna be for p hat? What is
Be
my,
point-
how
it'd
much?
be the square- It'd be the square root of 0.3 parentheses 1 minus 0.3
Which is 0.7.
divided by the number which is 1,000.
Yeah, dividing by your sample size, which is 1,000. On my calculator, 0.3 times 0.7 is 1,000 square rooted. Gives me approximately what number? Hopefully you're doing it too. Approximately what number? Anyone?
2.1.
I did not get 2.1. 0.3 times 0.7 over 1,000 all square rooted. I might have done it wrong. 0.3.
Oh, I didn't square root it. Oops.
Ah. I got 0.0145 approximately. Do you all get the same thing?
Yes.
Okay. So. Excuse me, we're looking for the probability that p hat is between 0.272 and 0.328. How would I calculate the probability that p hat is between, what does SRS stand for? It stands for simple random sample. Simple random sample. So what's the probability that p hat is between 0.272 and 0.328? How do I compute that?
Is p hat the one we just solved for?
P hat is, well, we don't know what p hat is. That's the whole point. What's the probability that if we get a p hat, it would be between those two numbers? That's what we're trying to calculate.
Okay.
Right? P hat is not something that we know in advance because it comes from our samples. So if I take a sample, p hat could be anything between 0 and 1 in theory. So the question is, what's the probability that it's going to be between 0.272 and 0.328? How would I calculate that?
Normal CDF.
Normal CDF. Because after all, we did decide that p hat is normal. With what mean, what deviation, what lower bound, what upper bound?
The upper bound would be 0.272. No, the lower bound would be 0.272, and then the
Lower-
upper bound would be
Yeah, would be
0.328.
excellent. With what mean and deviation?
The mean would be 0.3, and then the standard deviation would be 0.005.
Okay, so let's do it. What does our calculator give us?
I got 0.99466632853.
0.94, I'll just say 0.95.
Okay.
So in other words, there's roughly a 95% chance if the true value is really 0.3, then my sample would give me something between 0.272 and 0.328. And it's because the sample size was so large that I was able to do that. Because if I didn't have that information, I wouldn't know that it's normal. I can't assume normality for a small sample size, only for a large sample size. How large? We'll get into that as we go along. But certainly by 1,000, it's large enough. Yes, no, maybe so. This takes some time to assimilate. We finished 15, which is good because it's the last chapter of the test. All of next week is going to be review. Now, that does not mean I'm going to wait for you to ask questions. We're going to be going through problem after problem after problem from the various chapters at the ends and work our way backwards. If, we have time to get all the way back to chapter 1, great. Although I doubt we'll be able to in 2 days. But all of next week is going to be devoted to reviewing for the test, which is on October 19th.
What
Okay,
time is the test on the 19th?
well, I assume it's class time,
Oh,
right?
Okay.
I mean, 6:30, I mean, what time? Yeah, 6:30 to 8:10, right?
yeah.
Well, I'll have details for that, by the time we, as we get closer. But anyways, next week, no Scantron. I mean, if I haven't heard anything about a Scantron, if I make my own tests, they're not going to be Scantron based. And if I do not make my own test, I'll let you know. If you need a Scantron, and you can always buy it like from the bookstore, like 5 minutes before the test. It's not shouldn't be a big deal. But I'll have to email my boss to find out if I'm writing my own or not, or if he's going to provide one. Anyways, so I'm going to stop recording now.